Today we will discuss estimation of parameters in the case of multivariate normal distribution. So we have to have a sample first, and on the basis of that sample we will try to estimate the mean vector and the variance covariance matrix. So let me have O1, O2 up to On as IID observations coming from p-variate normal with mean vector mu and variance covariance matrix sigma. So what I know is in this mean vector mu, I have mu1, mu2, mu p. So basically I have p unknown parameters here, and in the variance covariance matrix sigma, I have sigma 11, sigma 12, sigma pp, sigma 1p, then sigma 2p, sigma 33 up to sigma 3p, sigma pp. So either this entire upper diagonal or entire lower triangle can be considered as unknown. So the total number of unknowns I have is 1 plus 2 plus up to p. So p into p plus 1 by 2. These many unknowns I have in the variance covariance matrix. So my job is to estimate this mean vector and variance covariance matrix. We know that in the univariate normal setup, sample mean is unbiased estimator for population mean. So let us first check whether that is true here also. So we define sample mean O bar as 1 upon n sum over I going from 1 to n OI. So if I want to compute expectation of O bar, I will have 1 upon n summation I going from 1 to n expectation of each OI, which we know is mu. So this becomes n mu upon n, which is mu. Therefore, sample mean is an unbiased estimator for population mean even in the multivariate normal setup. In fact, we haven't used normality here, so we can say that in general, in a vector setup, sample mean is unbiased estimator for population mean. Now I have to worry about variance. So what we know is this sigma 11 is actually variance of the first component, sigma 22 is variance of the second component, sigma 12 is covariance between first and second component, and so on. So in general, we know that sigma ij is covariance between ith component xi and jth component xj. Okay, so if I say that all these are coming from distribution of x, so if I say that x has distribution np mu sigma and O1, O2, On are just realizations of x, so O1, O2, On are observations coming from distribution of this x, then sigma ij is covariance of xi, xj. So in the univariate setup, we know that sigma ij can be estimated as 1 upon n minus 1 summation xi minus xi bar and xik, let me call it, and then xjk minus xk bar, where k goes from 1 to n. Okay, so we consider all possible, we consider kth pair on ith and jth component, and we consider, this is xj bar. Okay, xik minus xi bar, xjk minus xj bar. Better to write in terms of oi oj, so it would be easier. So if I write in terms of oi oj, it would be, so if you are getting confused with the notation, just ignore this. I have 1 upon n minus 1, k going from 1 to n. I want covariance between ith and jth component. Okay, so if I have O1, O2, On, where my O1 is written as O11, O12 up to O1p, okay, and this way, if I have my first observation as O11, O12, O1p, then here I want jth component of that. So OKI minus OI bar and OKJ minus OJ bar. Okay, OKI is ith component of kth observation and OKJ is the jth component of kth observation, and we are trying to compute correlation between them. Is it okay? This is very important. Now, what do I know? I know that this sigma I hat j hat is actually unbiased for sigma ij. So we generally denote this by Sij. So we know that this Sij is unbiased for this. So can we have something similar in the vector setup or in the multivariate setup? So for that, let us first define a matrix called as CSSSP matrix. What is meant by this? This is corrected sum of squares and sum of products. Okay, so what do I mean by this? So if we define matrix S as sum over k going from 1 to n OK minus O bar into OK minus O bar prime. Okay, we are defining a matrix S as sum over k going from 1 to n, OK minus O bar, OK minus O bar prime. Let us check the orders first. OK is the kth observation, which is of order p cross 1. O bar is also p cross 1, so this is p cross 1. This is its prime, so 1 cross p. So basically for every observation we are taking product of that observation with its prime and we are subtracting the mean first, and then we are taking sum over all possible observations. So sum of such p cross p matrices, finally my S is going to be of order p cross p. This S is actually called as CSSP matrix. Why? First of all, corrected. Corrected means we are subtracting mean, so it is corrected. Sum of squares and sum of products. Now, when I take this, I'm going to get some components will be squared. So when I say okay, let me write. So for example, if I consider O1 minus O bar into O1 minus O bar prime, what do I get? So first O1 minus O bar is O1 1 minus O1 bar, first component of O bar, then O1 2 minus O2 bar up to O1p minus OP bar, where O1 bar, OP bar, O2 bar, OP bar, these are components of O bar. This into O1 1 minus O1 bar up to O1p minus OP bar. So if I consider this product, what do I get? Let me just consider the matrix product. So first entry is going to be this into this. So I have O1 1 minus O1 bar whole square. Here I would have this into second entry from here. So O1 1 minus O1 bar into O1 2 minus O2 bar, and so on. Last entry would be O1 1 minus O1 bar into O1p minus OP bar. This is the last entry in the first row. Here I would have O1 1 minus O2 bar into O1 1 minus O1 2 minus O2 bar into O1 1 minus O1 bar. So basically this entry. Here I would have O2 2 minus O2 bar whole square, and last entry would be O1 2 minus O1 bar into O1p minus OP bar, and so on. So the last entry would be OPP minus OP bar whole square If you want to write this entry, it would be O1P minus OP bar into O11 minus O1 bar. Okay. So this is how my first matrix in this sum would look like. Now you can see here I have squares, I have products. So corrected squares, corrected products, and we are going to take sum over all such things. This is just first. So in general, I am going to write my S as sum over k going from 1 to n OK1 minus O1 bar square, then OK1 minus O1 bar into OK2 minus O2 bar, and so on. OK1 minus O1 bar, OKP minus OP bar, and so on. Last entry would be OKP minus OP bar whole square. Okay, so this matrix is sum of squares as well as products. Hence it is known as corrected sum of squares and sum of products matrix, that is CSSSP matrix. Now from this CSSSP matrix, can I get unbiased estimate? So let us check. So we know that this sum can be taken inside, and hence every entry here, if I divide by n minus 1, becomes an unbiased estimate of sigma. Okay. If we don't want to use component wise argument, okay, first let me write component wise argument, that ijth entry of S divided by n minus 1 is actually sigma ij from univariate properties. Okay. There is another way to define it, and it is slightly more precise. So if this is my S matrix, and let me consider L prime x, we know that L prime x will have univariate normal distribution with mean L prime mu, variance L prime sigma L. This I know. Because this is univariate, now I know that expectation of L prime SL, if I consider, of course when I divide by n minus 1, what will it be? Okay, expectation of L prime SL divided by n minus 1 would be L prime sigma L. This is again from univariate properties, because L prime SL upon n minus 1 would be unbiased estimator for L prime sigma L, where this S is the CSSP matrix. Okay. Now using this, I can say that okay, every component of S when divided by n minus 1 would give me the desired estimator, because if I put L equal to 1 0 0 0, then L prime SL is actually just S11. So I would have S11 upon n minus 1 as unbiased estimator for sigma 11. So this would give me that L prime SL upon n minus 1, expectation of that is sigma 11. This comes by substituting this L. So in general, if I define L as 0 1 1, where this one is at say ith position and this one is at say jth position, then L prime SL would actually be L prime SL, I would get sigma II plus sigma JJ plus 2 sigma IJ. So of course when divided by n minus 1, this I would get. I know from this earlier setup that okay, sigma II sigma JJ can be estimated by using 1 in L at ith position and jth position. So I can prove that okay, Sij upon n minus 1 is an unbiased estimate for sigma ij. So as I said, you can either go by this component wise argument, or you can first define L prime x to have just univariate normal distribution with mean L prime mu, variance L prime sigma L. Then because L prime sigma L is variance in the univariate case, it can be estimated in an unbiased manner by L prime SL upon n minus 1, and by substituting different L's, so taking L with 1 in ith position or taking L with 1 in jth position, I can get unbiased estimate for sigma II, sigma JJ, and then taking L as having 1 in ith as well as jth position, I can prove that okay, Sij upon n minus 1 is an unbiased estimate for sigma ij. Therefore, what I have is S matrix, the CSSP matrix divided by n minus 1 is an unbiased estimate for sigma. So this is how we get unbiased estimate for mean as well as variance. But we know that many a times just unbiased estimation is not enough. We want to go for maximum likelihood estimation. So if I want to go for maximum likelihood estimation, I will need to write down likelihood first. Then we will take log likelihood and we will solve the equations and we'll try to get maximum likelihood estimates for mean and variance. So for writing likelihood, I need PDF. First of all, I hope everyone remembers what is a likelihood. Likelihood is actually related to probability. So it will give me, in maximum likelihood estimates, what we try to find is, we try to find those values of parameters which are most likely to have generated the current sample. So current sample is given to us. So we try to find which values of mu and sigma are most likely to have generated the current sample. So we know from the PDF of multivariate normal that for a single observation, PDF can be written as 1 upon 2 pi raised to p by 2, then determinant of sigma raised to half, e raised to minus half, oi minus mu prime sigma inverse oi minus mu. This we know is a PDF for single observation, ith observation. So my likelihood is going to be product over I going from 1 to n of this. Okay, so my likelihood is product over I going from 1 to n, 1 upon 2 pi raised to p by 2, sigma raised to half, determinant of sigma raised to half, and is e raised to minus half. So I can take product inside, so I would have 1 upon 2 pi raised to np by 2, determinant of sigma raised to n by 2, e raised to minus half, summation I going from 1 to n, oi minus mu prime, sigma inverse oi minus mu. Okay. But generally we take log likelihood because it is easier to maximize log likelihood. So let me do the same thing here. So log of L would be minus np by 2 log of 2 pi minus n by 2 log of determinant of sigma, and then minus half summation I going from 1 to n oi minus mu prime sigma inverse oi minus mu. Okay, so this is my log likelihood. Let me call it 1. We have to maximize this log likelihood with respect to mu as well as with respect to sigma. Remember, mu is a p cross 1 vector and sigma is a p cross p symmetric positive definite matrix. So we have to estimate all those parameters by differentiating this. Now, if I want to differentiate this first with respect to mu, let us say, another assumption that we are going to make is sigma is not a function of mu. Okay, so when I differentiate with respect to mu, sigma won't come in picture, and when I differentiate with respect to sigma, mu won't come in picture. sigma and mu are not functions of each other, they are just constants. So of course we should somewhere mention that mu is anywhere in Rp and sigma p cross p is symmetric positive definite matrix. Okay, so if I differentiate with respect to mu, what do I get? D log L by d mu. My first term is free from mu, so nothing. This term is also free from mu, so nothing from here. So from here I would get minus half as it is, summation I going from 1 to n, and now inside the sum I need to differentiate with respect to mu. So this is a quadratic form, so we know that the derivative will be 2 times sigma inverse oi minus mu, and because mu is with a minus sign I would have minus 1. So my 2 gets cancelled, minus sign gets cancelled. So if I equate this to 0, I am left with sigma inverse oi minus mu sum over I going from 1 to n is equal to 0. 0 of course a vector because this is p cross p, this is p cross 1, so this 0 has to be p cross 1. And this is 0, not O. Okay, right hand side. So if I pre-multiply by sigma, then I will get summation I going from 1 to n oi is equal to n mu. Hence my mu hat turns out to be summation I going from 1 to n oi upon n. Okay, so my maximum likelihood estimate for mu turns out to be nothing but the sample mean O bar. So MLE for mean is just the sample mean. Now we have to worry about maximum likelihood estimate for variance. Now variance is sigma and we actually don't know how to differentiate with respect to an entire matrix. So we will try to differentiate with respect to components of matrix. But before that, to make things easy, let me define a matrix V as sigma inverse. Okay, so sigma inverse is V. As a result, my log likelihood becomes log L equal to minus np by 2 log of 2 pi. Sigma inverse is V, so if I want to take sigma inverse here, this would become plus because this minus 1 would go here, so this would become plus. So I would have plus n by 2 log of determinant of V and then minus half summation I going from 1 to n oi minus mu prime V oi minus mu. Okay, so we will try to differentiate this log likelihood now with respect to ijth component of V. So now V is involved in second term as well as in third term. First term anyway is not going to contribute. So we have to differentiate log of determinant of V with respect to Vij and this term also with respect to Vij. So let me first start by considering determinant of log of V with respect to ijth component of V. So how can I do this? We know that determinant of any matrix can actually be written in terms of ijth row or ijth column. Okay, so first of all, derivative of log of something is going to be 1 upon that thing into derivative of that thing, right, by chain rule. So this is 1 of, because I am differentiating log, I would have 1 by that and then derivative of that with respect to Vij. So what is derivative of determinant with respect to Vij? So for any matrix V, I can write determinant of V as sum over V Rj Brj. So determinant can actually be written as we fix some row or some column and then, so here I am fixing jth column and I'm writing determinant with respect to jth column. So R is going from 1 to P because my V matrix is P cross P. So I am writing determinant by fixing jth column. So VRJ, BRJ, where BRJ is actually the cofactor of VRJ. Okay, so by keeping rth row and jth column out, whatever remains, you take determinant of that. That becomes the cofactor, of course with appropriate sign. Okay, now if I use this, I'll have Vij as, now other Vij's are not going to contribute, so I'm going to get only Bij here. So only when R is equal to I, my Vij is going to be present here. For every other R, derivative is going to vanish. So I'll have determinant of V, its derivative as Bij, where Bij is cofactor of Vij. So substituting it in this, what I get is dabba log V upon dabba Vij as 1 upon determinant of V into cofactor of ijth entry. And this you know is nothing but ijth cofactor. So this is actually jith entry from adjoint of V divided by determinant of V. So ijth cofactor is nothing but jith entry from adjoint of V, linear algebra. So jith entry from adjoint divided by V is nothing but ijth entry from V inverse, because this is how you define inverse, right? Ijth entry from V inverse, and because V inverse is sigma, it is nothing but sigma ij. Okay, so dabba log V upon dabba Vij turns out to be just sigma ij. So even though it seems complicated, the answer turns out to be quite easy. So the second term differentiating with respect to the second term is done. Now we have to differentiate with respect to the third term. So in my third term actually the diagonal contains V. So let me just consider the inside term first. Okay. So let me consider as y minus mu V y minus mu. Now this I have to differentiate with respect to V. We know that y minus mu prime V y minus mu order is 1 cross 1. So since it is 1 cross 1, I can write it as trace of itself. So it can be written as trace of y minus mu prime sigma inverse, which is actually V, I'm sorry, we are writing as V, y minus mu. By the properties of trace, this can be written as trace of V y minus mu into y minus mu prime. Okay, by trace properties I can change the order. As long as I am going in a cyclic fashion, trace remains the same. So now if I take sum on both the sides, so taking sum over I on both the sides, what I get is sum over I going from 1 to n y minus mu prime V y minus mu. This is actually my term in exponent except for half. It is same as sum over I going from 1 to n trace of V y minus mu prime. Now trace can be taken outside the sum. So this can be written as trace of V sum over I going from 1 to n y minus mu into y minus mu prime. Now y minus mu into y minus mu prime is nothing but the S matrix, CSSP matrix that we defined earlier. So this becomes trace of V into S. Okay. No, wait. In my CSSP matrix, what I have is X bar. So let me try to bring in that X bar. So what I'll do is sum over I going from 1 to n, y minus mu prime. I will try to bring in the mean. So y minus o bar plus o bar minus mu, and then y minus o bar plus o bar minus mu prime. Okay, so I'm adding and subtracting the mean. So this becomes I going from 1 to n, y minus o bar. So I'll consider this as one term, second term, third term, fourth term. So I'll have y minus o bar plus o bar minus mu. If I take transpose inside, it will be oi minus o bar prime plus o bar minus mu, not bar, prime. Okay, so this becomes sum over I going from 1 to n, y minus o bar plus o bar minus mu into y minus o bar prime plus o bar minus mu bar prime. So if I simplify this further, I would have sum over I going from 1 to n. First term will be y minus o bar into y minus o bar prime plus second term will be sum over I going from 1 to n, o bar minus mu into y minus o bar prime plus sum over I going from 1 to n, y minus o bar into o bar minus mu bar prime plus sum over I going from 1 to n, o bar minus mu into o bar minus mu bar prime. Now o bar and mu are both constants, so if that can be taken outside the summation because it doesn't depend on I. Sum over I going from 1 to n oi minus o bar is basically sum of deviations of observations from their mean. Hence this sum is going to be 0, so this term will be 0. Similarly, by the same logic, this term will also be 0. So I am left with sum over I going from 1 to n, y minus o bar into y minus o bar prime plus n times o bar minus mu into o bar minus mu prime. But we know already that mu hat has been estimated as o bar. So when I am trying to solve both the equations simultaneously, I have to put mu equal to o bar. So this term will also become 0 and hence I am left with just s. Okay, this is nothing but s. So I would write summation I going from 1 to n y minus mu prime v y minus mu as trace of v s. Okay, now that it is written as trace of vs, can I differentiate it with respect to vij? Okay, so trace of vs will basically be sum over I going from 1 to p, or maybe I write sum over j going from 1 to p, the jjth element of the product vs, right? Jjth element of the product vs. What is jjth element of this product? So if we consider jjth element, how can I write that? So this would be matrix product. How do I write? VJR SRJ, R going from 1 to P. Okay. jth element can be written as VJR SRJ, where R goes from 1 to P. And now I have to differentiate this with respect to Vij. So I have derivative of sum over j going from 1 to P, sum over R going from 1 to P, VJR SRJ. Okay. So let me say derivative with respect to, in general, KL instead of Ij, because J I am using here. So from this derivative, only when I have KL here, means when J is equal to K and R equal to L, only at that time this will survive, VKL will survive, otherwise it won't. So I have dabba VKL, sum over J going from 1 to P, sum over R going from 1 to P, VJR SRJ. So it would survive only when I have KL, so I will have SKL. Okay, I will have SKL. So as a result, what I have, SKL is kth element of the CSSP matrix. Hence, now substituting it in my dabba log L, what I am left with is dabba log L upon dabba Vij. First term vanishes. For the second term, we know that the derivative is just sigma ij, derivative of log V, log determinant of V. But I have n by 2 sitting over here. So I will be left with n by 2 sigma ij, and from this term I have minus half and the current derivative. So I have minus half. So if I differentiate with respect to KL, I get KL. So when I differentiate with respect to Ij, I will get Sij. So Ij. And now I have to equate this to 0. So I am left with sigma Ij hat as Sij upon n. Okay. Hence, at least the solution to likelihood equation is sigma ij hat as Sij upon n, which is expected. CSSP matrix divided by n. Okay, does this complete my proof of MLE? No. So far what I have proved is the mean vector, sample mean vector, and Sij upon n, that is CSSP matrix upon n, they are solutions to likelihood equations. That much I have proved. But we know that just being solution to a likelihood equation is not enough. We need to actually maximize the likelihood, because solution can be minima also, or it can be a saddle point also. So in the next lecture, we'll try to prove that this solution actually maximizes the likelihood. Okay. Right now what I have proved is that till S CSSP matrix upon n and mu vector, that is x bar mu hat, is actually solution to likelihood equations. This solution maximizes the likelihood will be proved in the next lecture.
Thank you.